And I'm not sure what's going on, but let's go to the answers. Oh. Thought I already had to. Thank you for keeping it to me and not keeping it and saying, well, I'm just going to change the answers while he goes over the answers. Okay. Question number 1. At sunrise this morning, because I got to the gym before 6 and I look up in the moon. It was nice and clear this morning, unlike last night. And so the moon was a crescent above the eastern sky. Oops, I didn't say crescent here. That gives you part of the answer. It was about 45 degrees above the eastern sky. So, if you have the moon in the morning sky, what does that tell you about the phase? It's waning. And if it's close to the horizon, so we could instantly rule out all of those. And then if it's close to the horizon, it has just risen. If it's on the other side, it's been up a long time. It's just about to set. A full moon will rise at sunset and set at sunrise. This is rising close to sunrise, so it's a long ways away from a full moon, the crescent moon. And so it was the waning crescent. It's binary. Sorry. Number 2. How did Eratosthenes of Cyrene, chief librarian of the Library of Alexandria and the inventor of geography, how did he determine quite accurately the diameter of the Earth?
I think it was the angles and the shadows.
You are correct. Remember, he noticed that there in Syene or whatever, that at noon on a certain day, the shadow went all the way down to the bottom of the well. And so then he had somebody measure in Alexandria where the shadow went. And from those two, he got the size of the Earth. And so the shadow, which one was that? B. Okay, number 3, which is not a reason why the ancient Greeks rejected Aristarchus of Samos's notion that the sun was the center of the universe with the Earth orbiting around it. D. They did observe retrograde motion, but
They already had a model that explained it.
well, it was developing at that time. The Ptolemaic model that actually explained it wasn't there yet.
Is not. That's the key word.
Finally, which statement is true about gravitational force? It's always attractive. The only true force, we have a total of 4 fundamental forces. There's the strong force, the weak force, and the electromagnetic force.
Aside from the gravity.
Plus gravity, yes. So that's why, I think I mentioned that like the first or second lecture period, that there were 4 fundamental forces, and gravity is the one that I consider the ultimate winner in everything, because it's what holds the planets together, holds the stars to the planets, holds planets to the stars, I should have said. Yeah, it works both ways. It's what crushes stars to make, white dwarfs, black holes, neutron stars.
Will we talk about neutron stars?
We will, yeah. Okay, 2 clicker questions off the bat. Number 1, the first 2 are ones you've seen from previous lectures, just to make sure we're still up to date. What does Kepler's second law imply? The first law is that the planets do ellipses around the sun with the sun at one of the focal points. And the third law is that the period of orbit squared is equal to the semi-major axis cubed. We're asking about the second one, the other remaining one.
Is this a trick question?
Yeah. By the way, you guys saw the announcement. If you are Maggie, you have the wrong clicker. Or did you not buy one yet?
Oh, I've got one just here.
The clickers they just got in were the wrong ones.
Oh, for real?
For real.
I'm having worse with the clicker. Oh, not.
Cracker Pop Rice Krispies.
Not in.
Satish.
Okay, I'm doing it.
Okay, so you missed the quiz and you don't get to answer? That's the worst of all worlds. So is it the batteries are dead or what?
No, it's on.
Is it the channel? No, the new ones are little flat card things. And they're actually old ones. They sent us the wrong ones. Thanks. No dice? Oh, okay. Yours is different than the way I have registered for you. Okay. All right, we can change that. Okay, so, it didn't show me the, okay.
Good. Anyone got A's?
I don't know how to show data slice, view original chart. Show me the chart. I told it to show me the chart and it did. Okay, I can't see it showing me what you answered, so I will just write the correct one. I'm sorry that I can't have that. Kepler's second law implies that it's the one that says the area swept out per time is constant by a planet orbiting the sun. And so if it's going to sweep out the same area when it's closer, it's going to have to cover more distance in the same time. Thus, the planets go faster when closer to the sun.
There we go. Hey.
Yeah, I had to read read carefully there. Okay. We good with that?
I have a question.
Go ahead.
So the third and the second law sound super similar.
The third law has to do with the time for a complete orbit, not how fast it's going at any part of the orbit.
Has your size mainly, right? The size difference?
Well, the second law says that the planet that is
Closest.
while not that is closest, but while it's closest.
It's
So I have one
fastest,
planet.
correct?
One planet, when it gets closer, goes faster. When it gets farther away, it goes slower. And we see that significantly in comets. Remember when I talked about comets? When comets come in close to the sun, they whip by, and they're only close to the sun for a couple months. And then when they go away, they'll be out there for maybe 100 years, going super slow because they're so far away.
But they're still being acted on by sun gravity.
Yes. Yeah, the sun's gravity, remember the short range was one of the potential things on the quiz? Definitely wrong. The sun's force, while it's considered the weakest, or not gravity, considered the weakest is the longest range. Well, electromagnetics the same range, but it gets weaker as you go bigger because you tend to have charge neutral, whereas with mass it's always attractive, it just gets bigger and bigger and bigger. So the third law is about comparing the time it takes for planets to orbit and their distance. Now from last night's activity, which planets were going the fastest, had the greatest distance per month?
The ones that were closest.
The ones that were closest. So the third law ends up saying that the planets that are closer to the sun travel faster. But the second law says for a single planet, when it's closer to the sun, it will be traveling faster. Okay, next clicker question. Wow, I'm already, sorry, got to reopen it by accident. I just closed it when I hit the button.
Is that
that's the clicker question, and now you can answer. I had to reopen it on the computer. So we once again saw this before. The diagram below illustrates a portion, I don't think it's going to show me your answers on this either, honestly, of the model for the universe described by whom? Lauren, check your channel. 33, yeah. Okay, there we go. Boom. We're good now.
All right.
It once again didn't show me the answers. Well, I don't know. I don't know why it did, because it should have. Does this look like what we did last night? No, it does not. What are some significant differences between what we did last night and this? Yeah, the Earth is at the center here, and what we did last night had the sun at the center. So we can rule out the person whose model we did last night. Whose was it? Copernicus. So get him out of there. Now, have you ever learned of Galileo's model?
Not yet. Well,
Me either. Have you heard of Tycho's model? It exists. It's really convoluted, and we don't talk about it because it's so confusing. Not that one. So we're left with Kepler or Ptolemy. Kepler's model is, like Copernicus's model, heliocentric. What's the difference in Kepler's model and Copernicus's model? The ellipses is the primary difference that we would observe. And so what we did last night was circles. With Kepler, they're ellipses, which are pretty close to circle. You might remember the sizes, going around the sun. So we can rule out Kepler because they're still going around the sun. It's just ellipses, things that are a little off. And so we're left with Ptolemy. And remember, Ptolemy, we've got this weird thing. Because Venus and Mercury are always pretty close to the sun, they never get more than fairly small angles from the sun. Ptolemy's model had essentially a line drawn from the sun to the earth, and they're doing their epicycles about a point pegged on that line. So that was how he kept them from having, the big distances, the big elongations away from the sun. And then Mars is out here doing its circle, Jupiter, and so on. That's Ptolemy's model. We don't believe it, but it's kind of important to have the historical background and understand why people believe this for 2,000 years or so. You had a question, Kendrick?
yeah, is that like to scale? So Mars?
No.
Okay, that's not even.
Yeah, when you look at
I was like, okay.
its solar system models, they either show you the inner planets or the outer planets. Because if you can see the inner planets, the outer planets are way out there. And if you see the outer planets, the inner planets are all just a little blob in the center. So yeah, not to scale. All right, we've only spent 20 minutes. It's time to get started with the lecture. Did I show you this timeline before? I do not think I did.
No.
Okay. I was just checking because I wouldn't go over it again. To me, it's interesting to look at this, especially as you can see people who lived the same time, contemporaries. You see Martin Luther here was a contemporary with Copernicus. By the way, I must say I really enjoyed the sermon last week where he started talking about that castle and came around again to Martin Luther being there when he was, anyway, yeah, just have to show appreciation for a pastor. Michelangelo, Da Vinci, all the same time there's Copernicus and Columbus. He sailed the ocean blue sometime. Yeah. Okay, stay with me there. Sometime around there. And I've told you, right, I really hate that stupid rhyme, and so I say in 1493, Columbus sailed the Great Blue Sea. 1494, Columbus found the North American shore. You can make any old mnemonic you want. They don't have to be right. Okay, so we have Copernicus here. When Copernicus died is when he really publicized his idea of the heliocentric model. Now, he wasn't the first one with the heliocentric model. We could go all the way back to Aristarchus, who was a very strong proponent of the heliocentric model, but people weren't buying it back then. We have Tycho Brahe, who was essentially from the time of Copernicus up until about the time of, let's say, Guy Fawkes, whatever, died just a little bit after him, and Milton, he of Paradise Lost. Yeah. Anyway, okay, so let's get back to not worry about them. Tycho Brahe, very important. Why was he important? Not because the prosthetic nose.
Yeah.
Okay, he was famous because of the nova. And because of his fame, he got in tight with the King of Denmark, set him up with the world's greatest observatory, and he took very meticulous measurements of the positions of stars and planets. I always kind of lampoon him, both because, he felt that he had to have a duel about who's a better mathematician, and also because he was working with a very convoluted model that doesn't make much sense. He couldn't really find any reason or rhyme in his observations, which were extremely good observations. So after him, we had Kepler, who picked up his information and saw the patterns in the information. The very definition of intelligence is seeing those patterns. So Kepler had to be a very intelligent person. And notice Galileo and Kepler were contemporaries. Galileo was born a little earlier, died a little later. So they were living at the same time, and certainly Galileo ascribed to Kepler's understanding and helped in finding information to supplement Kepler's understanding. I did not show you, I skipped over some slides on Galileo, but Galileo, after he improved on the telescope, he used it to study, and he saw on Jupiter, right? I didn't talk about this, did I?
No.
When he looked at Jupiter, and one night he sees Jupiter, and he has marks in his books, and he says, I saw these things there near Jupiter. And then the next night I looked at Jupiter, and I had this. And he kept marking each night what he saw for Jupiter. And those things, there were always 4, well, sometimes 3, but they were moving around. And he said, this must mean that there are things orbiting Jupiter.
That must have blown his mind.
I don't know if it blew his mind, but it did blow everyone else's mind, right? Because I think he was probably already skeptical about a geocentric model. But to everyone else who said that everything's orbiting around the sun, around the earth, here he has evidence of things orbiting around Jupiter. And so if you have things orbiting around Jupiter, that means not everything is about the earth. And so that gave credence to the idea that maybe the earth itself is going around something like the sun. He also observed things like using his telescope, he looked at the sun, and yes, but he saw that the sun, had like sunspots, storms on the sun. We can't see those with the naked eye, right? You look at the sun, yeah, it starts to hurt, but you don't see dark spots on the sun. Now we have the song, there's a little black spot on the sun today, right? It's the same old thing as yesterday. Oh, wow. No, it's not. But they're also a good band. Yeah, I won't sing for you ever again. Or so you hope. He saw these sunspots, storms in the sun. He didn't know they were storms, but places where there were blemishes on the sun. And the Catholic Church had built the model that, based on Aristotle's ideas, everything out there was perfect. Now the moon, you can see that the moon isn't perfect. It's got things on it, right? And they say, well, that's easy. The moon's so close that the sin on earth has caused it to have some blemishes. But trust me, you go further away than the moon and it's perfect. And here he says, the sun's not perfect. And so that was another thing that, took a whack at the understanding that Christians had developed based on Aristotle's view. One of the other important things he noticed was looking at the phases of Venus and of Mars. If we look at Ptolemy's model, which will come up here in a few moments, if we look at Ptolemy's model, if you look at, for instance, Mercury, there is never a time when Mercury is on the opposite side of us from the sun, according to Ptolemy's model. Hence, there should never be a time when you have a full Mercury. It should always be, half Mercury or less that you're seeing lit up. And the actual fraction depends on, of course, the distances and the size, but it should never be more than a half Mercury. And so he observed the phases of Mercury and Venus and found that they went through a full cycle of phases. If they go through a full cycle of phases, that means that you have to have, at some point, it's on the other side of the sun, so either we're in opposition or it's behind the sun, conjunction, a superior conjunction. That couldn't happen with Ptolemy's model. So he got lots of information from his telescope observations to say that we couldn't have a geocentric model. That is, we can't have everything orbiting around the Earth. I know I did talk about him writing his book, and in his book, his friend the Pope said, sure, you can write the book, but you have to give my arguments. And so he had Simplicius, however you say his name, give the Pope's simple-minded arguments, and the wise man giving Galileo's arguments, and then the logical man always saying, yes, Galileo's arguments are right. And for that, he faced the wrath of the Pope, because apparently you're not supposed to mock the Pope. I mean, it makes sense, doesn't it, when you think about it? Okay, so here in 1632, he wrote his book, Dialogue, the dialogue between those three people. And here in 1633, he was imprisoned for mocking the Pope. It didn't take too long for that to happen. And then he didn't die until 1642, so he had about 9 years there. Kepler's laws are shown when he came up with them here, 1609 and 1619, for when he came up with his laws, so he didn't get them all at the same time. And then we have Isaac Newton. Isaac Newton is very, very important to us physicists because of his three laws of motion, of which you've already studied, right? You worked with them on Friday. We'll have a little more on them. And he lived the same time as William Penn. Hooray! Talking about America now. And we can see some other people here, George Washington, George III, George Bush. I don't know what number he would be. What? Oh, yes. I don't recognize the name Edward Teach, but I do recognize Blackbeard. Yes, it says both, for my sake, apparently. Okay, but it's interesting to see the timeline on the development of modern astronomy. Right? We talked about what was going on 300 years before the time of Christ. We work up to, and it's really only since around, let's say, 1600 on, so the last 400 years or so, that astronomy as we understand it has developed. And trust me, they weren't idiots out there doing the work. I mean, like, the work of Eratosthenes, pretty amazing. The fact that I've used up 60% of our class period, pretty amazing. So, Sir Isaac Newton. He's a sir because he's a knight. Not the kind of knight that goes and fights people and jousts, but the kind who is knighted because of the great advances that he gave to humanity. So, what did Newton write the most about?
I'm going to say gravity.
God. Yeah, he wrote the most about God. He wrote about as much about God as he did about all of his science stuff. But of course, he's famous mostly for his science stuff because he really was brilliant. Now, his childhood, have we talked about his childhood? Okay. He was born, his father died, his mother remarried. His mother's new husband said, I don't want that kid. And so he was raised by his grandmother. And he went to school and he was bored. I'm sure he was bored because I tried to put myself in his place. So he would go to school, instead of doing what the teacher asked him to do, okay, now everybody practice your numbers. He would be working on making little inventions to impress the ladies. And so when he was done with the compulsory, when he was done with the compulsory school, something like 6th grade, he got a job as a shepherd. So Newton the shepherd, he's out here, and what's a shepherd supposed to do? Watch the sheep. Much like the song goes, but I'm not going to sing it. But what he did was he continued to make little inventions because he was really interested in those while the sheep wandered away. So he was a failed shepherd and a failed student. And people said, okay, this kid's clearly brilliant. If we can get him to figure out what's important in life, we think he can go places. So he got support funding to send him on to higher education. And he was still kind of a goof off through his education until his last year. Some of you might be entering your senior year of college. And when you get to that point, you have these really weird ideas like, what am I going to do next year? I won't sleep in on the weekends. I won't, goof off. I'll probably have to have money. And so he realized either he was going to have to go get some job or he's going to have to straighten up and fly right. So his senior year, he got his act together, impressed the professor, got hired on to work as a house scientist for a professor, basically like a graduate student. And then the greatest thing that ever happened to Newton occurred. The Black Plague. Everybody cheered, right? Woo! Now, the Black Plague, you start having people die. Except for the guy that, I'm not dead yet. You will be. I'm feeling pretty good. I think I'll take a walk. You guys might have seen that movie. Anyway, so of course you don't want to have all the kids together and have all the kids die for your generation, right? That would be bad. And so they canceled school for like a year and a half. Wow. And so now if it was me, they canceled school. My sister lives in Huntington Beach. I'm there, right? I'm going to spend the next year and a half sitting on the beach, going out to Ruby's and having myself a burger every now and again. Newton says, oh, sweet Mother Mary, I can study physics with nothing to interrupt me. And so he goes back to his grandma's house and just studies physics for a year and a half. And during that year and a half, he came up with virtually all of his great discoveries. He did his work in optics. He developed calculus because the stuff he was doing, there wasn't math available to solve his work, so he invented a kind of math to solve his problems. He came up with 3 laws of motion. He came with the law of universal gravitation. And then he went back to school, didn't really write about it. He wrote an article and said, using this new math I invented, I can solve these problems. He didn't tell anybody what the math was about or anything, just called it this math of fluxions. So I think it was Leibniz, a French guy, came over and asked him about this new math. And he said, yeah, do this. And then the French guy publishes his work. So he's the first one to publish on calculus. Thus there's controversy about who invented calculus. Was it the person who said, I found this new method and explained it to somebody else? Or the person who he explained it to who published it?
Oh, man.
Anyway, and of course, it depends on which side of the English Channel, which one you believe is the inventor. So he came up with a lot of great stuff, and we're going to learn a little about his great stuff here in my 15 minutes remaining. So, before we get started with his laws, just to make sure we remember a very important word, acceleration. Yay. Acceleration is easy to get confused. I swear half of my physics class right now is still confusing acceleration with speed or velocity. Speed is how fast you are covering the ground. You cover more ground per second, that's a greater speed. Acceleration is how quickly your velocity is changing. Now, what's the difference in velocity and speed? Velocity is speed with direction. So if I walk like this at 2 miles an hour, and then I turn and walk like this at 2 miles an hour, those are the same speed, but different velocities because the directions I was walking were different. What was that? There would be an acceleration for when I stopped and turned and started. Yeah. So acceleration is anything that changes your velocity. So it could be either a change in direction or a change in speed would be an acceleration. Now, that's important because Newton's laws are what relate forces, things that push and pull, to acceleration, the change in motion. So let's look at Newton's laws. The first law, I believe I just skipped right over. The first law says that an object will just continue in constant motion, that is constant velocity, so the same direction, the same speed, unless something pushes or pulls on it, it has a force to make it change. The second law, usually written something like this, force net is equal to mass times acceleration. Now, your textbook doesn't put that net. You might have noticed on my grading of the Flip Fridays, I added the word net on virtually everyone's page because it really is important. I have a force of gravity pushing down on me right now. I have a force of the ground pushing up that's called the force normal, and those two add up to 0. So that if I stand here, I have a force of gravity down on me. I don't accelerate downward. I have a force normal up on me. I don't accelerate upward. The reason is because the sum of those forces adds up to 0. And since the sum of the forces, which is what net force means, is 0, then my acceleration is 0. I believe our textbook also prefers to write this as acceleration is equal to the net force divided by the mass, except for, of course, it doesn't say net. So we have practical examples. You have a man with a shopping cart. This is usually the state of the man with the shopping cart. An empty cart. Unless he's there with his wife. Then it becomes a full cart over the course of 4 or 5 hours. I really am anti-shopping. I sweat when I get frustrated, and if I go shopping, I sweat profusely because it's so frustrating for me. And hence... Hence I exaggerate on the time and whatnot because it seems forever. I didn't hear what Kendrick said, and I think it's better that I don't. So, Satish?
Okay, so, sorry, acceleration, just that concept in
Yeah.
general, is Newton's first law?
Well, Newton's first law says that there's no acceleration unless a force acts on you.
Oh.
The second law tells you how big the acceleration is if a force acts on you. So if you know the second law, it implies the first law already. So that's why I skipped over the first law. So you have a man pushing on a cart. If the cart is empty, it has a small mass. Mass is an important concept. It's how much stuff is present. So I have more mass than Cody, right? Yes. That's Dylan. That's Caleb. I have more mass than Cody. That just means there's more of me here than there is of Cody. Now, if we stepped on scales, we would also find that I weigh more than Cody. But if Cody and I were to then say, hey, let's go to the moon, and so we somehow magically get to the moon tomorrow, I would still have my same mass, he would still have his same mass. When we stepped on the scale, I would weigh less than he had weighed on Earth. Now, he'd weigh even less, but I would weigh less on the moon than Cody does on Earth. Because weight is a force, but mass is how much of you is present. And so when you look at this equation, force net is mass times acceleration. The mass is how much of you is there if we're talking about you. The acceleration to get the weight is the acceleration of gravity. And so you just take your mass times acceleration of gravity, and that tells you what your force is, what your weight is.
Yeah.
Question?
We can blame gravity for overweight people.
Yes, we can. But we have to blame gluttony for overmassed people. Okay, so the man pushes the cart that has not much mass in it. It's pretty empty, not much stuff in it. He pushes it, and it takes off. Then he takes the cart that has been filled with all of the good things in life, chocolates, whatnot. He pushes that with the same force. It has more mass. What does that tell you about the acceleration according to this equation? Same force, but if it has more mass, you divide by a bigger number, you have less acceleration. So it's harder to move that thing. Now, you know I like to play football. In fact, I love to play football. And it's harder for people to make me move than it is for them to make, let's say, my son move. He's 160 pounds or so. I am more. And so if you put the same force on him as you put on me, he's going to have twice the acceleration. He's going to start moving a lot quicker. There's also a little strength issue, but listen. Yeah. He's very proud. He's already, in the last month, increased his bench press by, I think, 30 pounds. So he's pretty keyed up this morning. Okay, so Newton's second law allows us to relate that acceleration to the force. Newton's third law says for every action there's an equal and opposite reaction. In that phrasing, action means force. Reaction means a returning force. So for every action, let's say that I push on this backpack. My push on the backpack is an action. There is an equal and opposite reaction, which means that backpack pushes on me with exactly the same force, but in the opposite direction. Now, this leads to some interesting things. You have up there the first picture, X and Y. Assuming they both have one X chromosome, but the girl has a second X and the boy has a Y. And so when she pushes on him, if they're about the same mass, according to Newton's third law, if she pushes on him, how hard is he pushing back on her? The same. So they have the same force. If their masses are the same and they have the same force, what does that tell you about their accelerations? The same. So they're just going to take off at roughly the same speed. Then you have Z. He failed in the chromosome lottery, apparently, because there's no Z. But he's much more massive. And so, well, yes, he's taller. He's also wider. She pushes on him with, how is his force? Now he's heavy. This is like Cody pushing on me. I'm Z. When Cody pushes on me, how hard am I pushing back on Cody? The same. And so, how do I respond to Cody's push? Much less, because I have much more mass. Now, it's easy for me to say these things and for you to agree with them as I say them, but then we ask other questions that are harder to answer. So let's take an example of, I am getting in a fight. Who wants to fight?
I'll fight.
All right, come on up here.
Oh no.
I'm not actually going to punch you. You're not going to punch me. At least that's the plan. I once did shadow boxing when I was in grade school. In a strobe-like thing. Yeah. Boom, I accidentally. Okay. So if I hit him, right, we're on here and I'm all, right?
I'd be so done.
So I hit him. My fist is here in his forehead. What's going to happen?
Your hand is going to foot.
My hand's going to hurt. His head's going to snap back unless you get those muscles all tightened up to try to prevent it.
That would be worse.
Who's going to take more damage? What do you think?
I think you.
It actually depends on where I hit. If I hit him here, I'm a real idiot, and it probably is me. Because that's a really hard part of the head. If I come like this, yeah, then his jaw would be all mangled, and my hand would probably do better. Why? Because harder part of the head versus weaker part. But about the force. So let's say I hit him in the jaw. So I'm, boom, right in the jaw. Right in the kisser. Or I could be clammed and, to the moon, Lucy. What is her name? Ethel?
Oh, yeah.
I pulverized his jaw. My hand comes out okay. What force was bigger? My hand hitting his jaw or his jaw hitting my hand?
Same.
It's still the same. That's all I wanted to say.
Okay.
It's still the same. A lot of times you think, no, the hand really destroyed the jaw. So the hand must have put a bigger force on the jaw than the jaw put on the hand. That's wrong. The forces are the same. So why did the hand pulverize the jaw? It's not the speed, it's the strength. This isn't as strong to an action like that as the fist is. Now, if I had hit my fist here, I would have had all kinds of broken metatarsals, you know. Yeah, or carpals, excuse me. Yeah. If I kicked him, yes.
So basically, like
Carpals,
it's not,
metacarpals,
the force of me pushing against the table, it's not the fact that I can't move the table. Like, I could move the table in one direction, and it's not the fact that the table isn't giving an equal force back. You think they cancel out? It's the fact that my hands don't go through the table.
Okay, when you push on the table, you're putting force on the table, it's putting force back on you.
If I move the table, there's still that equal force, but how am I moving it? Because when those forces cancel out.
No, because, okay, my teacher in grad school, he wrote a textbook. He had this question on a test that I thought was awesome about Mr. Ed pulling a wagon. I've actually seen it in other textbooks too. I don't know if he originated, but I give him credit. And so Wilbur tells Mr. Ed to pull this cart. And Mr. Ed, in his best Mr. Ed voice, says, "But Wilbur," going on in my voice, "I can't pull the cart because Newton's third law says the force I put on the cart is the same as the force the cart puts on me, but in opposite directions, so they always add up to zero. And Newton's second law says the net force is mass times acceleration, so if the net force is zero, then the acceleration is zero." That's basically what you're saying, right?
You should find that clip on YouTube.
Yes.
Now it's basically.
His name was Jamie Walker. So the problem with that analysis is, and I didn't talk about this detail of the equation. Newton's second law, you have to look at one object and say, what's the net force of that one object? So when you push on the table, let's say we're going to take your body as the object. We look at the forces on your body. Yeah, the force of gravity down, the force normal pushing you up, the force of the table returning to you. The force of you pushing on the table is acting on the table, not on you. And so if we look at the forces on you, in the horizontal direction, we only have the table pushing this way, and thus you accelerate. Now if we look at the table has you pushing this way, of course it has gravity down, force normal up, and then it has other things, rigidity, that are pushing it this way, so that the net force of the table remains zero even when you push. And so it doesn't move, it's not supposed to at least, when you push on it, but you do. Now, I am so close to out of time, I didn't want to end here, but I'll just go to tug of wars. I usually don't do tug of wars in this class, but we're having a good discussion. So let's say we have tug of war. We get my team of 5 people against your team of 5 people.
Oh, that's good.
No, we're not going to do that.
Oh.
How do you decide who wins the tug of war? I mean, not, okay, so you watch the bandana goes over here. But how do you look and say, I think that when I have this table against that table, this table's going to win? Mass. That's what it comes down to. If you are just on the gym floor, the team that has the most traction should win unless they're really a bunch of not strong people. Because each team is putting the same force on the road. By Newton's third law, that has to be true. And it's the team that's getting the most friction from the ground, the best traction, that's going to be winning. And the heavier the team is, the better their traction, unless, you have some weird thing like they're wearing moccasins today, or, So when they have tug of wars, you never think about this, but it usually just comes down to how much does that team weigh, how much does that team weigh. Okay.
And that's why seniors always win.
Yes, because you gain like 5 pounds every year in college, right?
Yeah.
I took that one real seriously. Okay. Have a good day. Have a good project impact tomorrow. And then we'll see you on Friday. Remember to do the pre-class thing before coming to class on Friday.
Is it posted?
Not yet.
Not yet.
But it will be by tonight.
What's the pre?
So you'll have Thursday to work on it. Project impact does not last more than like 4 hours.
Yeah. What did you say?
What's the pre-class?
Yeah, Friday.
What's the pre-class?